nature enjoys its giants. The fossil record is a graveyard of titans, and our oceans still hide the colossal. But beneath the skin of every living creature lies an invisible web of mathematical laws, an unyielding framework. We don't see 80-foot humans walking the streets. We don't see King Kong, and you've probably assumed it's just a lack of evolutionary luck. But the truth is far more sinister. The universe itself prohibits their existence. Physics and physiology have already written their death warrants. Time to go down the rabbit hole. To understand the biological execution of King Kong, we must first look at the geometry of our prison. Look around you. The world we perceive operates in 3 dimensions: height, width, depth. This triad dictates volume, the literal space an object consumes. Now isolate a single layer, a surface. Surfaces exist in only 2 dimensions, height and width. Your body is a collection of these 2-dimensional borders, each carrying a vital, life-sustaining duty. The surface of your skin dissipates suffocating heat. The microscopic sheets of your pulmonary alveoli form a massive border to capture oxygen and expel toxic carbon dioxide. The lining of your gastrointestinal tract absorbs nutrients and water. Even the surfaces of your joints are designed to distribute the brutal crush of your own body weight. Dimensions are the currency of life. And when you change the scale of a creature, the universe alters the exchange rate. Let us conduct a thought experiment. Take a standard gorilla, 2 meters tall, weighing 200 kilograms. Now let's forge a monster. We scale him up 10 times, transforming him into a 20-meter King Kong. To maintain his proportions, he must grow equally across all 3 dimensions. Height, width, and depth all multiply by 10. But here is where geometry turns lethal. Because volume is 3-dimensional, it doesn't increase by 10. It increases by 10 times 10 times 10, a factor of 1,000. Since mass scales with volume, our innocent 200-kilogram gorilla doesn't weigh 10 times more. He now weighs a crushing 200 tons. But what about his surfaces, his skin, his lungs, his joints? They only have 2 dimensions. They only increase by 10 times 10, a factor of 100. While the monster's mass exploded by a factor of 1,000, the infrastructure meant to support it only grew by 100. His surface area is now proportionally 10 times smaller than that of a normal gorilla. Instantly, a countdown begins. King Kong is trapped in a body that cannot sweat or radiate heat fast enough. His massive volume generates immense metabolic warmth, but his small skin surface locks it inside. He would literally cook his own organs from the inside out. Small creatures like mice have the opposite reality: massive surface area relative to their tiny volume. It's the reason a mouse can barely maintain a fever. Heat escapes them too fast. Elephants, the titans of our modern land, had to grow gigantic, sweeping ears just to artificially boost their surface area and survive the sun. Kong has no such luxury. His lungs, vastly undersized for his 3-dimensional mass, would leave him suffocating in the open air. And the surfaces of his joints, his spine, his knees, would be pulverized. They simply lack the surface area to distribute the agonizing pressure of 200 tons. But the tyranny of scale doesn't stop at anatomy. It rules the monster's hunger. Consider a 10-kilogram dog eating 300 grams of food a day. If scaling were linear, a 20-kilogram dog should require 600 grams. But nature doesn't calculate linearly. Instead of a 100% increase in food, the larger animal only requires 75%. This is the rule of the 3/4, governed by Kleiber's law. As an animal grows, its basal metabolic rate, the energy required just to exist in the dark, scales efficiently. If the universe were simple, our 200-ton King Kong would need to devour 20 tons of food every single day. But thanks to Kleiber's law, he gains a massive scale efficiency. He would only need a modest 1.15 tons, an incredible evolutionary discount, except for one fatal flaw. Remember the surfaces? Kong's intestinal surface area for absorbing nutrients is still 100 times smaller than required for his mass. Even with a lower caloric demand, his digestive tract simply cannot process over a ton of matter through such a restricted biological border. There is a poetic rhythm to this metabolic scale. The heartbeat. If you count the total number of heartbeats across the lifespan of almost any mammal, the number is eerily similar. A mouse and an elephant are given a similar wealth of heartbeats by the universe. But because the mouse's metabolism burns with a frantic, chaotic heat, its heart races at a blinding speed. It burns through its biological bank account quickly, living a brief, fleeting life. The elephant's heart beats in a slow, stoic rhythm, buying it decades. But even if Kong's heart beats slowly, his architecture remains doomed. He is weak. Proportional strength fades as size ascends. Think of a structural pillar. If you have a massive column, its strength lies entirely in its cross-sectional area, a two-dimensional surface. If you cut that pillar's dimensions in half, its strength drops to a quarter. Strength scales to the square. Mass scales to the cube. As a creature grows, its weight outruns its strength by a factor of 10. The skeleton becomes a fragile cage. Without massive pillar-like legs, similar to a sauropod dinosaur, a 20-meter gorilla would be instantly crushed by gravity, collapsing into a tragic heap of broken bone and torn muscle under its own weight. As Galileo Galilei noted centuries ago, the smaller the body, the greater its relative strength. This shatters the myth of the miraculous ant. We are told ants possess supernatural strength because they lift 50 times their weight. They don't. They possess the exact amount of strength physics dictates for their tiny scale. If a human were shrunken to the size of an ant, they would lift the leaf just as easily. If an ant were magnified to our size, it would instantly die, broken by the atmosphere. When humans ignore this law of scale, tragedy follows. In 1962, researchers wanted to test the effects of LSD on an Asiatic elephant named Tusko. To determine the dosage, they used a linear calculation based on what a domestic cat receives, 0.1 milligrams per kilogram. They multiplied that by Tusko's 3-ton mass and injected him with a massive 300 milligrams of the drug. The calculation was an execution. Tusko collapsed almost instantly, suffering violent, catastrophic seizures. In less than 2 hours, he was dead. The scientists forgot that drugs are absorbed and metabolized by surface areas and metabolic rates, which grow much slower than sheer body volume. A linear calculation in a non-linear universe is murder. So, where does the terrestrial kingdom truly end? The largest land animal known to history was the Patagotitan majorum, a massive dinosaur weighing roughly 70 tons. A true miracle of biological engineering. Yet, it was nearly 3 times smaller than the Hollywood myth of King Kong. The great sauropods did not break the laws of physics. They lived on the razor's edge of what land gravity allows. To truly escape the prison of the square cube law, life had to leave the land entirely. The blue whale, weighing up to an astonishing 190 tons, It is the largest creature to have ever existed in the history of the Earth. But it cheats. It lives in a liquid void 100 times denser than air. The buoyancy of the ocean acts as an external skeleton, cradling its immense weight and saving its bones from the crushing reality of gravity. Yet, even in the deep, the rule of surfaces and volume commands. No fossil, no legend, no ocean depth has ever revealed a creature larger than the blue whale. It is the absolute wall, the final boundary allowed by the physics of our planet. Monsters do not terrorize our cities because the universe acts as an invisible warden. The math is absolute, the geometry is fatal, and the laws of physics remain undefeated.